and welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but still want to be its friend.
I'm Connie. I am definitely overwhelmed by the universe, but I do want to be its friend.
That's good. And I'm your friend, and I'm the universe's friend, so I know that you two can be great friends.
Yes.
Hi, everyone. I'm Dr. Moiya McTier. I'm an astrophysicist, a folklorist, and a good friend to the universe, and someone who likes to bring all of my friends together, like our fellow friend to the universe, our patron Scott C. Reynolds, who inspired today's episode topic.
Thank you, Scott.
Thank you, Scott. We got this question, what are the different subfields of astronomy, like the different broad domains of research interests under astrophysics? And I think that's a great thing to explore, especially for people who are earlier in their careers and are thinking about getting into the field maybe, or just casually researching the field and don't know what all there is out there. So yeah, this is a good place to start. So I'm curious, Bestie, what would you name? If I asked you what the broad subfields of astronomy are, what would you think?
Okay, so would space travel be under, or is that more engineering?
This is up to you.
Okay, so something in that arena. I wonder if it's stars versus planets.
Okay. Versus.
Well, not versus, but there's a stars subfield and a planet subfield. That's where I've got 3 ideas.
Cool.
That's about it.
Cool. Well, it does depend on who you ask if you're looking for the official list, but I think that your 3 is a good start. If you ask NASA, then you are going by their science mission directorates, and they have the Earth Sciences Division, the Planetary Sciences Division, that focuses on planets in the solar system that are not Earth. Then there's heliophysics, which is physics of the sun, astrophysics, which they define as, quote, the branch of astronomy concerned with the physical nature of stars, galaxies, interstellar clouds, and other objects, including their luminosities, temperatures, densities, and chemical composition, end quote.
Whoa.
That's what astrophysics is, according to NASA.
I would have split that up.
Yes. NASA also includes space technology in their mission directorate. So, yeah, like space travel stuff.
Yeah, the ability to get there in addition to all the stuff that's already there.
Yes, you have to get there in order to study it in some circumstances. And I want to use this as an opportunity to point out that NASA is not an astrophysics organization. They are not even an astronomy organization at its heart. Nowhere in NASA's name does astronomy or astrophysics show up. It is the National Aeronautics and Space Administration. And so that is why they lump all of the astrophysics together, because that's what NASA is known for, but that is not how NASA identifies itself. It's like if you had someone in high school who was a bully and a jock, and they were like, no, but I'm also an artist, because they were in one school play.
Okay. But for them, that's how they see it.
They see themselves as an artist. Yes.
Right.
Yes. So that's if you ask NASA what the different subfields of astronomy are. If you ask the International Astronomical Union, which is probably a better resource for this because they actually have astronomy in the name, then they have a few different categories as well. They focus on fundamental astronomy, which is tracking the positions of things that you can see in the space and cataloging them by their brightnesses and how they move across the sky. Then there's high energy phenomena and fundamental physics. So that's going to be your X-ray stuff, your black holes, your supernovae, your particle accelerators, probably any sort of particle physics going on. Then the next category is sun and heliosphere. The heliosphere is the entire region of space that's under the sun's influence. So that includes our solar system and the Oort cloud and really just out until another star starts taking over gravitational influence.
Okay.
And then there's a section or a committee for planetary systems and astrobiology.
Okay.
And then another for stars and stellar physics. Another one for interstellar matter and the local universe, which is a really broad category because you're talking about the space between stars all the way out to galaxy clusters. And then there's a section for galaxies and cosmology. I think that that's a really comprehensive list.
Yeah. And galaxies and cosmology, is that like a more high level view? Because it seems like it encompasses some of the other categories, subcategories.
Yes. Some of the things that are covered under high energy phenomena are smaller than galaxies. They are within galaxies. But as we're going to discuss later, the study of galaxies themselves, like galactic astronomers, it's not that they study everything within galaxies. It's more like they study how galaxies act as a whole system.
Okay, gotcha.
And then how galaxies interact with other galaxies. And so maybe by interstellar matter and the local universe, the IAU means like real local.
Yeah.
Like very, very within the Milky Way. But those are not how I would break it down.
Oh, we've got an exclusive proprietary list here.
This is, this is my podcast. And so I have to break it down how I see it. And I found 6 different categories.
Okay.
When I searched through my experience of astronomy. Personally, I tried to do research in as many different subfields of astronomy as I could when I was in college. And that's because I was very lucky. I had access to a lot of different research opportunities. I did not hit all of the different subfields, but I think it's really common for people to do their first research experience in galaxies, for example, and then they just study galaxies for the rest of their lives if they become an astronomer. And I think you need to try out galaxies. You need to try planets. You need to try some black hole stuff. And then you'll have more information, more context to make the decision about what to study for the rest of your life. Because as I'm going to point out throughout the episode, these fields, these subfields have different cultures. They have different traditions. They have different methods that they use, different ways of thinking. Yes, we're all astronomers, and so we're all cooler than physicists, but we do still have differences within our community.
Of course.
You can tell I'm going to be throwing some shade in this episode.
I see,
perhaps.
And I'm excited for it, to be honest.
So we're talking about the different subdomains of astronomy in terms of topic, but you can also imagine that there are differences in astronomers based on the methods that they use. So in terms of methods, you can have observers, people who do analysis on data from telescopes and instruments that observe the night sky. You can have a theorist who does a lot of calculations, a lot of math-based work, but that's kind of separate. That is distinct. There's some overlap, but it's distinct from computational astrophysicists who do a lot of simulations that are based on equations, but it's like digital analysis of equations instead of doing things on the back of the envelope by hand, which at least my favorite theoretical cosmologist, Dr. Chanda Prescott-Weinstein, that's how she prefers to do her work.
Nice.
So we have observation, theory, computation, and then the fourth very special thing, instrumentation, where you are actually building the instruments and the telescopes. I guess within computation, there are people who don't use the simulations, but they build the software packages themselves. And so building an astronomer is kind of like building a D&D character where you have to pick both a race and a class. And so I think that the race that you can choose, like you can be an elf or a dwarf or a dragonborn or something. I think your race is like the method that you use. That's if you're an observer, a theorist, or a computational astrophysicist. Okay. And then the class that you have within a role-playing game is what you do in your day-to-day life. And that you can be like a druid, you can be a rogue, you can be a paladin, a holy warrior or something. And I think that's like the topic that you work on. You can be a theorist who does stars or a theorist who does planets.
Yes, as someone who recently got into that kind of class system, I haven't played too many role-playing games, but I started playing Baldur's Gate, so this makes sense to me now.
Great. Fantastic. Okay, so now we're going to get into my list of subfields, which is, I guess, my list of classes for astronomers. I have 6 of them. And you and I talked before this about things that come in groups of 6. I would love for us to tag each of these subfields as one of the 6 characters from Living Single, which is a show both Connie and I have seen. I don't know how many of our listeners have seen it, but it's like Black Friends, but
Yes.
it came first.
But it came first.
It's like Friends is white Living Single.
Yeah, that's the actual framing of it. Because
Yes.
it came out the year before on Fox for, I want to say 6 seasons, 93 to 98. And
Yeah, it was a while.
it's like friends who are living in New York City. They're in Brooklyn. They live in a brownstone together. And so that's very exciting. Yeah, great characters.
So
Yeah.
the 6 characters are Khadijah, played by Queen Latifah. The cast is fantastic, but
Yeah.
I don't know all of their names off the top of my
Yeah.
head. I know that Max is Erica Alexander.
Yes.
Powerhouse. Love her. So we have Khadijah, we have Max, we have Regine, Sinclair, Kyle, and Overton. And I'm going to describe the subfield of astronomy, and Connie has to choose which Living Single character it reminds her of. And she does have to do it as we go through without knowing what all the subfields of astronomy are, but I will let her go back at the end and make one switch if she
Okay.
wants to.
Great. Appreciate
You're welcome. I'm so generous and merciful.
it. Indeed.
Okay. I also want to say, as we're going through these subfields, that I tried to imagine a data visualization. One thing that astronomers love to do is visualize data. And so if I had to make a visual representation of the subfields of astronomy, I thought about a graph, like a table or chart. I thought about maybe some sort of scatter plot. No, it's more like a color wheel. And how all of the colors of the wheel blend into the next color, even at the beginning, like where it starts, it kind of like it all blends back together. That is what astronomy is like. And the way I've organized it, I think you'll be able to see that the fields that I list next to each other are the ones that will collaborate the most. They usually will do the most with each other. But the first and last fields, they really have a lot of overlap too. So it is really a circle that rounds back on itself. It's an Ouroboros. It's a snake eating its own tail. Yes. So we're starting with particle physics.
Okay.
For each of these, I'm going to say what they do, their common methods, some of the astronomers that I either know or know of within that subfield, and then what I think their reputation as a subfield is.
I think
for
that'll be the
particle
part that
physics-
will help me the most decide which character they are.
I think so too. For particle physics, they are really trying to nail down the standard model of particle physics. We did a whole episode on this, episode 69, where we then decided what the nicest particle was.
I was going to say.
So we have filled out a lot of the standard model of physics of particles, but not all of it. And so the particle physicists are trying to do that, fill in the blanks. They are the astronomers / physicists, and they really ride the line between astronomy and physics. They are thinking about quantum stuff. They're thinking about the really tiny things and the fundamental particles and how they are related to quantum field theory. The particle physicists are thinking a lot about dark matter and dark energy because we don't know exactly what types of particles make up dark matter, and we don't know exactly what types of particles are driving dark energy. Do you have questions, Bestie? You have a question face.
Well,
Or are you just taking everything in?
I'm taking everything in
Okay.
because it might be too much for this particular moment to dissect some of it. So I'm just taking it in and deciding
Okay.
on character alignments.
Great. Okay. So they're concerned with dark matter, dark energy. They want to understand how forces work. As far as we understand, there are 4 fundamental forces that drive everything in the universe. The nuclear forces, weak and strong, and then electromagnetism, which is what, Bestie?
Light?
Yes.
Okay.
Yes.
Pop quiz and I passed. Yes.
You did. I knew you would. And then the 4th is gravity. But gravity is different from all the other forces in that for those ones, we've found particles that carry that force. Like the photon is the particle that carries the electromagnetic force. We haven't found something like that for gravity. Although if we do find one, we already have a name for it. We would call it the graviton, but we haven't found it yet. So particle physicists are trying to do that or come up with some other explanation. They are really trying to understand the creation and destruction and evolution of particles, starting from the Big Bang with like Big Bang nucleosynthesis. How were the very first particles formed? Why was matter ever so slightly more dominant than antimatter? They're trying to answer that question. And then tiny things in our universe today, like cosmic rays and neutrinos. Neutrinos are very small fundamental particles that can't be broken down into smaller pieces, and they're produced by high energy events like supernova or gamma ray bursts. And we just have a lot more we want to learn about them. So those are the questions particle physicists are trying to answer.
Okay.
They are lucky among astronomers in that they get to be experimental. They get to not directly interact with a lot of their source material, although we're made of particles. So, like, yes, they do. But they still have to be indirect and creative in a lot of ways. Often they are trying to study a particular type of particle, like the Higgs boson particle, for example. The Higgs boson is really unstable. It doesn't last very long in nature. So once it's produced, it will decay into something else, or it will produce other particles, and often we have to study those other particles that are produced instead of the main one we're looking for. But that's the beauty and creativity in science.
Of course.
And so they are using particle colliders, particle accelerators. This is the Large Hadron Collider at CERN. We should absolutely do an episode on that at some point.
Yes, please.
It's not the only particle accelerator, though. It's the one that gets the most PR, but there are others around the world. Apparently, there's one at Brookhaven National Lab in New York. The relativistic heavy ion collider is one of the biggest research particle accelerators in the U.S. So, yeah, thanks, Brookhaven. And then if you want to get to really cool places, you could go to the Ice Cube Neutrino Observatory at the South Pole.
They named it Ice Cube? Is that an acronym?
I think it is. Let me check.
Just because I know. I've learned in the last like 20, 30 episodes that you love an acronym, but also it being at the South Pole is incredible.
It is not an acronym.
Wow.
It was just us being clever and cute.
I love it.
But this is a picture I've included in the notes for you, Bestie, of Ice Cube, because this thing is huge. So I'll describe it for the listeners. Most of it is underground. It takes up, I can't even remember, but it's like a square kilometer underground. It goes almost 2,500 meters deep, and the whole thing is made up of tubes of light, tubes that can detect light and then are really sensitive. So they have to be under a lot of ice so that they don't get a lot of stimulation, like they get overstimulated easily because they're trying to detect these tiny little neutrinos. And
there must be a lot of them because if it's light.
The neutrinos aren't light. They actually don't even really detect the neutrinos, but when the neutrinos interact with water molecules in the ice around the detector, it produces other types of particles like electrons or muons, and those are easier for this to detect. But just to give you a sense of the scale, in this image, like most of it looks like this big hexagonal prism. That whole thing is underground. On top, there's a surface of ice, and there's a tiny little box in the center at the top of the image. Do you see that? That tiny little blue box in the center?
Yeah.
That tiny little blue box in the center is the entire Ice Cube laboratory where real humans go in and do their work.
That's crazy. It's giving Fortress of Solitude very heavily, and I'm pretty sure that anybody who works there probably does feel like they work for Superman. Like, I would love that for them.
Yeah. Yeah. I think that this is maybe one way I could cross the Antarctica off of my bucket list.
Yeah.
But I think the most realistic way is doing one of those cruises, one of those Antarctic cruises where I'm I give talks about space, or I lead them through stargazing or something.
Would love.
Would love. It'd be real cold. I would literally just do it to cross Antarctica off the list. But I love to complete things.
Yeah.
Okay, so particle physicists, they, like I said, they kind of ride the line between physicists and astronomers. And so a lot of the popular physics bros that you might have heard of, like the very popular science communicators, they are usually particle physicists and or cosmologists, which we'll get to at the end, because again, it's the snake eating its own tail. So some people who are pretty firmly particle physicists: Michio Kaku. He's a theoretical physicist who works on string theory, so trying to figure out what is the most fundamental shape and nature of particles in the universe. And then the Bryans. Brian Greene is also a string theorist, and Brian Cox does particle accelerator stuff when he's not being a British musician. He doesn't stop being British. He just puts the instruments down occasionally. And I'd say their reputation as a field is that they are the most physics-y of the astronomers. And so they're kind of intense. They are super dedicated to the work, and they do kind of make it their whole personality.
Okay.
So
I think
which
I'm ready.
character do you think it is?
I think it's Kyle, because Kyle is a Wall Street guy. He's like a guy, like that's his personality, is that like he has a great job and like is a ladies' man until he like accidentally falls in love with Max. So like I think Kyle, because like makes it his whole personality, but also you don't really know what he does because it's Wall Street. Like just one of those people where it's like the job title doesn't really make sense when you unless you like are in the know, kind of like particle physics. But like they also are the people who are like, I'm an expert in this. Like I'm a particle physicist, and those are the people we do see on the like we know particle physicists in like pop culture and stuff. So it's like, yeah, I think it's Kyle because of that. Like he's just like, yes, I work at Wall Street and I make this money and yes.
Oh, that's a good Kyle Barker.
Listen, those episodes with him and Maxine, you know, when they're first starting to hook up, it's just like he starts to use that really deep voice.
Yes, he does.
It's just like, that's nice. That's real nice. He knows
And
what
the
he's
laugh.
doing.
Oh, he still has that laugh because they have a podcast now. They have it's like Still Living Single or something.
Something like that, yeah.
He still has that laugh, and it warms my soul.
It's very delightful. That podcast I haven't watched the whole thing or checked out a ton of it, but I do like that they're doing it and they've been able to like get Queen Latifah on and stuff.
Yeah.
So it's a fun time.
We should go on and tell them which subfields of astronomy they are. Also, you were spot on. I was thinking maybe Max, but no, you're so right. Particle physics is definitely Kyle.
To me, they're not argumentative enough, but I feel like there will be something.
Ooh, okay.
So I was like, I got to save Max. I'm not ready yet.
Okay, all right. Well, let's move on to our second subfield, near Earth and solar system stuff. I feel like there are probably people who, like how you said and how I agree, NASA lumps too much under the astrophysics category.
Yeah.
People probably think I lump too much into this because it's the entire solar system. Including the Earth.
I mean, they have a galaxies one, or the IAU has a whole galaxies one. So, like, I feel like that covers a lot too. So it's fine.
It's fine. So under this category, this is where we study the Earth as a planet. This is climate studies. This is seismic studies. This is understanding planet evolution, so we know how much our human action is deviating Earth from its natural course of evolution. This is asteroid detection and tracking for both defense and mining, because we want to be able to divert any asteroids that come our way. We did that with the DART mission, the Double Asteroid Redirection Test. Another thing we have to do an episode on. And in terms of mining, I remember hearing conversations about that in college. So this is a decade ago at this point that undergraduates were doing research projects on asteroid mining. So I know that there are rich people who are working on it now.
Yeah.
This is where we are trying to understand and characterize the other planets. And this is where I would put all of the space launch stuff. I wrote in my notes, this is the NASA shit.
Love it.
Yes. Near Earth and solar system is NASA shit. And they're so lucky because they usually have a way to directly and up close study their targets. They can get like up close observations because they study things in the solar system that we send real telescopes to. If you're a scientist who studies Jupiter, if you study the Saturn moon system, you have the Juno mission, you have Cassini and Voyagers, and you have so much data that I don't have as someone who studied exoplanets. So they're very lucky. Nice. I think that I actually rushed this section because I just wanted to get to the exoplanets, and so I only wrote down one person. My bad. I'm so sorry, planetary astronomers out there. I respect the hell out of you. And I want to shout out especially Mika McKinnon, who is my favorite disaster geophysicist and sci-fi consultant. She was a consultant on Stargate SG-1. And if you watch Stargate, a lot of the equations that you see written on the boards behind them in meetings and stuff, that's Mika McKinnon's handwriting, baby.
Wow.
So she's really cool. Wendy Bohan is a geologist that I know. But the geologists would not consider themselves astronomers.
Yeah, I was going to ask about the difference, because there are the sciences of the people who study the things on Earth, but then these are scientists who are studying it, but as a planet,
not necessarily.
Okay.
I think that the geologists are not studying Earth as a planet. They're just studying Earth.
No, yes.
And I think that probably
So
most of
difference.
the people at NASA are not studying Earth as a planet, but astronomers will use that data when we are doing discussions about planets. I used Earth data when I was doing a project to figure out how we could measure the bumpiness, the topography on planets in other stellar systems. And I used Earth data as a point of an example of how bumpy a planet can be.
Yeah, I love that as the intercommunality of science, because we talk here about astrophysics, but you do use data from other fields of science in order to inform astrophysics, and that's really cool.
Yeah, it's interdisciplinary research is not only good for the scientists who do it, because it's good for our brain, but it's the world is interdisciplinary. So we humans love to put divisions between things and categorize stuff into different boxes. So I did think of some. Ashley Walker is an astrochemist who studies Titan and the clouds on Titan, and that's all I got. Okay, so their reputation and culture. Again, I think the people who study Earth probably don't consider themselves astronomers, so they might see themselves as the cool, maybe not the cool kids, but they see themselves as the black sheep. Some of them. I would say there's near guaranteed public interest, but it could go either way because a lot of people don't care about climate change. So
there.
So I'm actually going to take that back.
There's that.
So they do not have near guaranteed public interest, but they in other countries do have funding.
Yay for them.
I've got to stop talking now. Who do you think this is?
I got you. Okay, so I did want to, as I do these, I do want to shout out the people, because we are talking about the podcast and stuff. So Kyle Barker is played by T.C. Carson, because I'm on the wiki. Okay, so the one that I think is this one is Overton. So that's played by John Henton. And I say Overton because he's a handyman. He's from the country. So he's a down-to-earth kind of guy, okay? Everybody needs handiwork done at some point, so near guaranteed public interest in it. Probably doesn't think of himself, like, he doesn't really think of himself as, like, that guy. Like, he's just, like, a simple guy. Like, he's, like, low-key, like, stays close to the ground. You know, like, I think I think it's Overton.
You're so good at this. Yes, that's exactly what it is. Thank you. Okay. So now
This is so fun.
Good. Now we are in my domain. We are in my subcategory. It's planets. It's exoplanets, but planets in general.
So the previous section are the planets in our solar system, and then this section is planets outside of that.
Yes, but we do study planets outside of the solar system to learn about our own planets. And
Fair.
so the planets in the solar system are definitely included in the knowledge, and they will inform a lot of our understanding of other planets in other systems because we have a good view of the planets in the solar system. And so they speak to each other, and that's why I put them next to each other. What we learn in both will inform what the other does.
Absolutely. Gotcha. Thank you.
Of course. Thank you for asking. So I did not do any research with SETI when I was doing my studies, but there is a lot of overlap between exoplanet research and SETI work. The SETI Institute, the Search for Extraterrestrial Intelligence Institute, was started in the 60s by radio astronomers who studied stars, but were really interested in things like astrobiology and the habitability of planets. And so it's very interdisciplinary work, the SETI stuff, but it, I think, sits most squarely within the planets category. This is where you get intersections with astrobiology, like I said, with astrochemistry, because we are interested in the chemistry of planets, and the chem and bio can help us try and check for life on other planets. We can look for chemical signatures or biosignatures on other planets. Not much ethnobiology, not much trying to understand the cultures on other planets, although I just saw on their social media that SETI is launching a new research arm into Earth Society's response to first contact with aliens.
Ooh.
And that's really interesting to me.
That is interesting. As someone who likes movies and pop culture and stuff, like, I could imagine, like, going through those movies and stuff, and someone who's obsessed with what you do, like, how other cultures in the past have thought about this is very cool. So that is awesome.
Yeah. Like, I want to get involved in that.
I say go for it.
Cool. So it's not all about aliens, although I think that's where the public interest intersects most with exoplanetary research. But we are also trying to study other planets to learn how planets evolve, to get a better understanding of what to expect for the future of our planet and the other planets in our solar system. They have so many different methods of detecting exoplanets. We did a whole episode about it, episode 20. But as a recap, there are a handful of methods for finding planets. You could do it with radial velocities, which is when you look for the little wiggle dance that stars do when they're being tugged by the gravity of the planets around them. You could look for transits of planets where they block some of the star's light as they pass in front, and we can measure basically how big the shadow is to study the planet and the system. There's direct imaging, where you take just a direct picture of the exoplanet, but most planets won't let you do that because they're small and don't emit their own light. So it really only works with the hot Jupiters and the ones that are close to their stars, but not too close that the star overpowers their brightness. And then there's microlensing, where you have to, I guess, get lucky enough that a planet passes in front of some distant object, like a star, and that the planet's gravity bends the star's light around it and redirects it towards us, so that it briefly makes the star appear brighter than it actually is, because more of its light is pointed at us. That's microlensing. And then astrometry. I think we've only found a handful of planets using this method so far. It's where, so I talked about the wobble of the star when the planet tugs on it for radial velocities. With that method, we're looking at the star dancing towards and away from us. With astrometry, you're watching the star dance side to side and up and down. But it's actually much harder to see that in the signal because of the way the math works. It is much harder to see astrometry than radial velocities, but with the full Gaia data release, which should be in the next couple years, we will, we think, find thousands of planets using the astrometry method.
Wow. Wow.
Very exciting. Very exciting.
Wow.
So that's detection. That's just finding exoplanets. And we found the first exoplanets in the 90s, and around then it was, you find a new planet, it's very exciting. You find a new planet, it's very exciting. Eventually we got to the point where finding the planet wasn't adding that much individually. It was a drop in the bucket. And then we could do population statistics on them, which is great because it just gives us a better understanding of the whole picture. And instead, the focus turns to characterizing the planets, trying to figure out what their actual surfaces are like. And to do that, we have to get creative. You look for different types of signals in the light curve. I talked about my exotopography project. That was looking at the tiny amount of scatter that we would expect at the bottom of the light curve when the planet is actively passing in front of its star and rotating. And so some mountains are coming in and out of view, thus changing the amount of light blocked from the star and creating like a little jagged pattern in the light curve. And if you can remove enough noise from the signal to reveal just that little pattern left behind, then you can get a sense for how bumpy the planet is, how mountainous the planet is. And that type of creative use of data that we've been using since the 90s is what we expect of exoplanetary scientists. So you could get creative with the light curve. You can get creative with spectra from these planets. I never used this method myself, but I think it's so cool. There's this method called transit spectroscopy, where as a planet is transiting in front of its star, you look at it in different wavelengths and you measure how much light it's blocking in different wavelengths, because depending on what is in its atmosphere, it's going to look thicker or thinner at different wavelengths, because different materials are opaque in the optical, but they are transparent in the infrared, for example. And so if you can get the apparent size of the planet's silhouette at different wavelengths, that gives you an impression of what types of molecules are in its atmosphere. Yeah. I just love how creative we get. And so there are basically as many methods to study planets as there are planetary astronomers, which is great. Although we do have this saying, know thy star, know thy planet. And so astronomers who study planets kind of have to also be comfortable understanding stars. And so there's a lot of interplay between planets and stars, and that is the next category we'll talk about. Although I have this fun graphic for you that shows the different planet-finding space telescopes and the timeline of them. So starting with Hubble in 1990, which wasn't explicitly a planet-finding telescope, but we can now use it to study some planet atmospheres, all the way up to, I think, Corot might have been the first like explicit exoplanet finding mission, but it's not. I don't think that's a NASA mission. And then we have Kepler and K2, which was the most successful planet finding mission up until things that are active now and still going. And so I look at this and I feel so much optimism. Like there are just so many of these missions that thousands of people have collaborated on to build the machine, to launch it up into space, and then to analyze the data. And it's just like a beautiful collaboration. I'm really into it.
Yeah, especially across all the races of types of scientists, the computational, the... But yes, you would have to go like the wide spectrum of those different categories for this kind of work.
Yes, the observers, the theorists, the computationists, and the instrumentalists. Yes, for sure. For people that I know, I obviously know mostly planetary astronomers. I'd say mostly planetary and galactic astronomers. My main advisor in grad school was David Kipping, who is known for his work with exomoons, trying to find moons around planets around other stars, which is very hard to do. But he also has a reputation for just encouraging kind of out of the box and kind of out there thinking. If you are his student and you want to do a project looking for planets in the center of the galaxy, which has never been done before, David would absolutely say, yeah, Moiya, you can do that. Like take a week to see if it's feasible. Take a couple months to see if there's anything more to explore. Like, he's really good at just letting someone's intellectual curiosity roam, which is great in an advisor.
Yeah. Absolutely.
Another Dave, gotta shout out another Dave. David Charbonneau is the first person to have found a transiting exoplanet. He was one of my advisors in college. He's very tall. He's like 6'4", and I think maybe Canadian.
He was closer to see him.
He was. That's good. Yeah, he didn't have to look through as much atmosphere.
No. Hold the telescope up higher, that's great. Sounds great.
You're right. So he is very nice, very nice. And then there's Jason Wright, who's done a lot of work with SETI, and I think he won the Drake Award a couple years ago and has done a lot with astrobiology and habitable planets. Lisa Kaltenegger just published a list of the most habitable worlds, the 35 most habitable worlds, most Earth-like worlds, and so I've been planning an Earth-like worlds episode for a while, so that's going to be really useful for that episode.
Ooh.
Mm-hmm. Jesse Christensen is leading the NASA Exoplanet Archive, which I think everyone should check out. Dakota Tyler, another one of my SciComm buddies, just got his PhD where he studied exoplanet atmospheres and how planets around certain types of stars can lose their atmospheres at different rates, which is really interesting. So many.
I've seen Dakota
people.
on the TikToks.
Yes. There's a soft spot in my heart for Dakota because I met him when he was, I think, still in undergrad and starting out with SciComm. And every time there's something in California, which is where he was based, I would send it. When there was something in New York where I am, he would send it my way. It was nice.
Nice.
Yeah. Their reputation is that it's coming from the fact that they are one of the younger fields. The first planet was found in the 90s, and so you could not be an exoplanetary astronomer more than 30 years ago.
Wow.
And for that reason, it was one of the more popular fields for a long time. It was one of the fastest growing subfields. At least I don't have any data to support that, but that's how it felt when I was going to conferences. I was meeting a lot of early career folks who were interested in exoplanets. When I started at Columbia as a grad student, my advisor, David, was the only professor there who did exoplanet stuff. And he had at one point 6 different grad students in his research group. There were only 3 people in my grad school cohort, and 2 of us worked with David. So there were a lot of people who really wanted to do exoplanet stuff. And so they are, for a while, and recently, they were the cool kids. I think of them as like Gen Z, young millennials of astronomy. They were kind of in the move fast and break things style, but now they're starting to get more established, and they're like, maybe we have to be a little bit more serious.
Okay, so I don't know if I'll switch this later, but I'm going to go with Khadijah James, aka Queen Latifah. And I say that because when you're looking for exoplanets, you're looking for a new story. And as a journalist, as a magazine writer, she's always looking for a new story. There are many ways you could get that story. There are many ways you could tell those stories. So I think it kind of works into her career as someone who's always looking for what's new, what's hot. Her magazine was called Flavor Magazine, which is great. So that has that youthful edge. Because these characters are Gen Xers, I think, if you do the right math.
Yeah.
So we don't have a true youth. We do have a youthful presence, but I think Khadijah works for this one.
I think that's a good call. I wasn't sure what was going to go here. Hi, Hi, everyone. It's me, Moiya. Connie is writing an email to the Reliving Single podcast production team to tell them what subfields of astronomy all the cast members are, and I'm so certain that the actor who played Kyle is going to be really pleased with his assignment. But while she's composing that, I wanted to share some messages with you, the first message being a big thank you to all of the patrons who support the show financially every single month. We're an independent podcast, so we really need and appreciate your support. We also want to give a special shout out and a huge thank you to our Sun-like stars. Thank you to Scott Reynolds, Tom T, Seven Petrichor, Ashley Shambo, Bruce Sedloff, and Kelly Bonnell. You are perfectly golden, and we love you and thank you very much. You too can hear your name on the show. You can make it onto the patron star chart and get research notes for most episodes for $5 a month by joining at patreon.com/palebluepod. And if a monthly subscription isn't something you're interested in, you can make a one-time donation and become a supernova in the Pale Blue Pod sky at the PayPal link in the episode description. Of course, if you can't support us financially at all, we understand. Things are hard and money isn't the only way to help us. You could rate and review the show on whatever podcast platform you use. I also love reading those because it helps me understand what you like about the show and what we can maybe tweak a little bit to make it better for y'all. But no matter what you can do for the show, thank you for listening. Connie and I are honored to be a part of your week. Thank you so much. My next message is a podcast recommendation for another show in the Multitude Collective called American Medieval. This is a podcast about the Middle Ages, but with an American twist. Every week, Professor Matthew Gabriel is joined by an expert scholar to talk about either some bit of the medieval world itself or how Americans have, throughout our history, used the Middle Ages to say something about ourselves. They just did an episode about video games set in or around the Middle Ages, which was really fun, so you can check it out. New episodes come out every Wednesday. You can look for American Medieval wherever podcasts can be found, or by checking out AmericanMedieval.com for more. That link is in the episode description if you, like me, also struggle to spell medieval. All right, Connie has sent the email. I really hope they get back to us. Regardless, let's keep talking about subfields in astronomy. The next category is stars, and when I was preparing for this episode, I had to sit for a second and think, what do I say besides they study the stars? Like they're trying to understand stars and how the stars are.
It's pretty simple,
it's pretty simple.
Like, yeah.
Yeah, they're trying to understand the stellar evolution cycle, how they form, and what different parameters change what their lifespan is going to be. So right now we understand that the mass of a star when it first forms is really influential in the story of its life. We know that low mass stars are going to fuse hydrogen for much longer than the high mass stars, but we do not know exactly what the mass distribution of star formation is. We have a good idea, at least in our local universe, that it's the 70 to 75% M-type stars. It's maybe 5 to 10% stars that are a little bit more massive than the sun, but we can always nail that down more, and we aren't sure if it's the same in the rest of the universe. So they're also trying to figure that out, trying to figure out if there are any sort of trends, star characteristic trends throughout the galaxy. And to do that, they can use a lot of ground-based telescopes. So there's a lot of ground-based observing. Although like Hubble looks at stars, JWST looks at stars, Gaia mapped more than 1 billion stars in the Milky Way. So definitely a star-based space telescope. They will look for the brightness and the spectra of these stars. The spectrum of a star can tell us its temperature. It can be a proxy for its mass. It can provide the surface gravity, the strength of gravity at the surface of the star. And I did not understand how you get that from a spectrum when I first started out in astronomy, but because of the weird, intense nature of stars, they are such extreme environments that there are different rules of physics that apply there that do not apply here on the surface of Earth. And under those rules, the pressure at the surface of the star is going to be proportional to the surface gravity. But just around the surface of the star, not further down. So if you have more pressure, then you have more interactions between particles near the surface of the sun. And when those particles interact, they're going to get excited, like atomically excited, like their electrons will go to higher energy levels, or they might separate from the molecule altogether. And when you have excited particles in a spectrum, when you're measuring excited particles with a spectrum, the line that you see, the spectral line, doesn't look as sharp. It widens, it broadens. So you can tell by the width of the spectral line how strong gravity is on the surface of a star. Isn't that fucking insane?
Wow.
I love how we learn these things.
Yeah.
And then obviously with spectra, you can learn like the chemical composition of the star, and you can get radial velocity. So you can get an idea of how far the star is moving towards or away from you. And that's just with the spectra. You can also learn cool stuff with the brightness. And if you get modeling involved, which a lot of stellar astronomers do, then you can learn even more. Some of the more popular stellar modeling codes out there are MESA. MESA stands for the Modules for Experiments in Stellar Astrophysics, and it lets you model individual stars' evolution along different, like you can track stars of a certain mass, stars of a certain temperature, stars of a certain age, and it shows you how those stars evolve if you give it like initial conditions.
Okay.
And a lot of stellar astronomers are maybe not trying to complete, because it's pretty complete so far, but like understand the physics that explains the Hertzsprung-Russell diagram. The HR diagram is one of the most, I almost said famous. One of the,
I was like, okay.
like for astronomers,
Yeah.
this is one of our most famous graphs. It really is.
And I was like, who?
My bad. It's a graph of temperature versus brightness for stars. So temperature is on the bottom axis, but it's backwards. So hot is on the left side and cold is on the right side. And on the vertical axis, it is brightness of the star, but it goes in the normal way. So the top is brighter. And on this graph, the vast majority of stars, like 90% of stars, fall within what we call the main sequence. These are the stars that are actively fusing hydrogen in their cores. And once you stop fusing hydrogen, you move away from the main sequence. And the path you take depends on your mass. So if you are a star that's kind of like our sun, around the 6,000-ish Kelvin mark, when you stop fusing hydrogen in your core, you veer away from the main sequence and you become a white dwarf. So there's this whole little cloud of white dwarfs. There's a whole little area on the graph where stars can become white dwarfs at a range of temperatures, but a much smaller range of brightnesses, which you might see in the chart. Mm-hmm. See how there's more spread on the temperature axis, but they're really close on the brightness axis? Yeah, exactly. Mm-hmm. If you are a little bit more massive than the sun, then you can leave the main sequence and become different types of giants. A little bit more massive, and you might become yellow, orange, or like red giants. If you're much more massive, then you can become blue supergiants, even further up on the Hertzsprung-Russell diagram. And so we understand, based on observations, what happens to stars at different snapshots for the most part. But we are still doing a lot to understand why, which I find really exciting. And the people that I know, I had one advisor who was like a stellar chemist. His name was Keith Hawkins. He was a cool dude. He's now at UT Austin, I think. And then Tabby Boyajian is a, quote, famous, unquote, astronomer. She published this paper in 2016 about a star that was changing its brightness really rapidly. It, over the course of less than a year, was changing its brightness by like 20%. And we didn't know why.
Higher? I mean, brighter or dimmer? Or fluctuating?
Fluctuating.
Oh.
Yes.
That's
extra weird.
unsettling. Yeah.
And just for context, a planet, even a massive planet, is only going to dim a star by a few percent. Like a Jupiter in front of a star like our sun would dim the sun's light by a few percent. 20% is extreme. So the community was all aflutter about Boyajian's star for Dr. Tabitha Boyajian, I should say. And I think a big part of that was the title of the paper. Like, the star is interesting, but back in the day, we used to be able to give our papers interesting titles. So her paper was called Where's the Flux?
I love that.
Yeah. And then my favorite star paper is actually a review of methods to find the ages of stars. It's called Ages of Stars, published in 2010 by David Soderblom.
That's the one. Yes, that's the title.
So straightforward.
Sure.
For their reputation, the stellar astronomers, they're the old school astronomers. They're the OGs of the field. They move slower. They're more methodical. It seems like they care more about doing things right instead of like experimenting and trying new stuff, because they've been around for a lot. Like Galileo was a stellar astronomer.
Oh, okay.
Yeah.
I think this is Maxine Shaw, attorney at law. Played by Eric Alexander. I was going to go a different direction, but your description of them being like old school astronomers, being slower, methodical, being like attentive to details, having to sort of like know all of these like different rules of like how the stars, which directions they go and all that stuff. And I feel like that's good for a lawyer. And just Maxine is just like a down to business kind of person. So I love that. But she also is like fun. She has like her showy side, which is great because you're studying stars, which are delightfully bright in the sky.
Great answer. Bestie, I realized that I miscounted and there are 7 of them.
Okay.
I promise. I know
fine.
how to count.
It's okay.
It's okay. It's okay. Thanks, everyone. The next category is transients and compact objects. These are things that might be there one moment and aren't there the next. And or they're things that are so heavy they're going to be there forever. So this is stuff like supernovae, gamma ray bursts, any sort of collisions of massive stuff. So if you have black holes colliding or neutron stars colliding. Honestly, sometimes I just interviewed someone about a paper they wrote on potential planetary collisions. And that would also, I think, be seen as like a transient, but it would be transient mixed with stellar.
Right. The collabs would have to be like going real fast. Like, okay, call up your buddies in this department, call up your buddies in this department because we got something crazy going on. So
yes,
let's collab.
Yes, bestie. And in fact, this is, I think, the subfield of astronomy that has the most quick response follow-up. I remember having a professor in college who was a supernova astronomer, and he had a pager on him at all times. Probably not all times, but like during the day, he had a pager on him in case a supernova went off because the brightness for a supernova, it can diminish by a lot within the first day, depending on what type of supernova it is. And so you really have to go and look at them quickly. And so they have networks where they are alerted about a supernova and then they go and react by turning another telescope towards it. This is also like the multi-messenger events that astronomers get excited about, like when you can see from a black hole merger or from a neutron star merger, you can see the gravitational waves and you can see the light from the event, from the collision. That's called multi-messenger, and the transient people love that. They love that.
Of course.
Because their stuff is transient. So you need to get as much information about it as quickly as possible.
That makes sense.
People I know in this field, Kip Thorne is a black hole astronomer who is a consultant for Interstellar. I met him in an elevator once, and we had a lovely chat about the weather. It's very bland stuff. Another astronomer, Dr. Jedida Eisler, studies blazars, which are the brightest, most energetic black holes. They're shooting off these jets of light. That's a quasar. If the jet of light is pointed in our direction, so it's just like boom in our face and it looks really, really bright to us, that's called a blazar. And Jedida Eisler...
Blaze it.
Yes. Jedida Eisler studies blazars. And she's fantastic. When I was struggling around grad school application season, and when I got my first rejection from a grad school, it was Jedida that comforted me through it.
Nice.
And I made her a character in the science fiction novel that I wrote in college.
Love that.
And then Serafina Nance is also a good friend of mine, another science communicator, and she studied supernovae, also published a book, a memoir, where she talks about her life and supernovae and like explosions in space. I think it's called Starstruck.
Great title.
So their reputation, these transient people, they're flashy. They're like the special teams in sports terms. They are the cool kids because they show up, they get the job done, and then they go party.
Okay, yeah. So I've been feeling very strongly, and that confirmed it. This is Regine Hunter, played by Kim Fields, because she is a fashion superstar. So like all the glitz, the glam, all the wigs, like she just loves to like change her look up and stuff. So it's about things that are like, trending fashions, what's in, what's out. But also a thing that I remember the most about Regine is that she's always out the door. She's always just like, "Hi girls, okay, I'm leaving now, bye," and then just out the door. Like she's always just like in and out. And so the way she does it is like so chic. She's just like, "Okay, I have to go now." And so I think she'd be these transient and compact object.
Oh, brilliant. Yes. Yes. So right. I think at the end of this, you'll have to, I don't know, pick one that isn't a character. You'll have to kick one out. Yeah. Yeah. Okay, so the next step is galaxies. The galactic astronomers study how galaxies change over time, how they form, how they merge with each other. They study the different behaviors of galaxies by their morphological class. So we tend to categorize a galaxy based on its shape, if it's a spiral galaxy or an elliptical galaxy or lenticular galaxy or irregular or something. And that sounds mean, but they do behave really differently based on their shape. And so the galactic astronomers are trying to study that. They use systems thinking more than other types of astronomers. So like this is a mindset that they have to have, because a stellar astronomer, they study a star. They might study like a system of stars that orbit around a shared center of mass, but they are still individual stars. A planetary astronomer might study a whole system of planets, but they are still individual planets that are distinct from each other with a little bit of influence. A galactic astronomer has to think of how everything within that galaxy is going to affect the overall nature of the galaxy as a whole. You have to think about the kinematics of the galaxy. How do the stars orbit around? Like that's a big deal. These galaxies are made of stars and dust and gas. So the way these things move will change its shape, which, as I said, determines a lot of the galaxy's nature. They also have to think about the chemistry and the chemistry over time and the chemistry in different places. You have to think about gravity in a more three-dimensional way. And in a non-symmetric way often, because gravity still works on stars, it still works in systems of planets, but simpler. Stars are spheres, so that it's spherically symmetric gravity. Even systems of planets, the gravity is like two-dimensional, but in a galaxy, it's 3D, and it's very confusing, and it requires a lot of heavy math. Also, there are just a lot of things moving around, so galactic astronomers rely a lot on simulations and models, and they also rely a lot on citizen science. Zooniverse is a massive citizen science platform. It's now extended far beyond astronomy. You can help out with biology projects. I think they even have some like literature ones, where the whole point of Zooniverse is that there are projects with too much data for the researchers to comb through. And so they put it up on Zooniverse and ask for people to help them with their analysis. And they give you instructions based on what the project is. But it started with a project called Galaxy Zoo, where there was an astronomer who had too many pictures of galaxies. And the point of the project was to classify the galaxies based on their morphological shape, based on what they looked like. And this was before AI, this was before image recognition, where the researchers needed people's help classifying the galaxies by eye, by their shape. And from Galaxy Zoo, citizen science has blossomed, but now there is still like I'd say a strong tradition of galactic astronomy using citizen science, which is great.
Yeah, that's very cool.
And speaking of Galaxy Zoo, I don't know why, but the only galactic astronomer that I wrote down, because I know others, but the only that I wrote down is Chris Lintott, who studies galactic chemical evolution and was the person who manages Zooniverse these days. Their reputation, their culture, the galactic astronomers, I'd say that they used to be the cool kids, like in the 50s and 60s, because we didn't even know that there were other galaxies aside from the Milky Way until the 20s. There was what we call the Great Debate in 1920 or like early 1920s, where we knew that there were, we called them nebulas, like fuzzy clouds, like the Andromeda Nebula, but we weren't sure if they were outside of the Milky Way or if they were within it. And that wasn't cleared up until the 1920s. And so in the 50s and 60s, this was still a relatively new field. They were like the exoplanets of their day. And so they were like hippies, but they were hippies in the 50s and 60s. And now it's the 2020s and they're like 70 or 80 years old. And like I don't want to hang out with the average. They're in their 70s and 80s, and I guess you could say they're kind of old-fashioned.
Ah, gotcha. Okay. So because there's an extra one, I'm going to throw in a spanner of Scooter.
Scooter, yes! Scooter.
And I didn't remember that much about his character because he comes in and out, and I just know he's Khadijah's love interest. But according to the wiki, he's like a music producer. He scouts new talent. He lives in LA but comes to see Khadijah every so often. He wants to go on tour with this band. And so like that gives me systems thinker. He got to coordinate a lot of different things. And I feel like he's into the music industry because he wanted to be an artist. Like, I don't remember that from the plot, but it's sort of like, you know, like young black guy who wanted to be an artist and then just like didn't hack it in that space, but then like helps to manage everything else. So that that's the closest I can think of like used to be a hippie, but like is kind of set in their old school ways, you know, because I know a few people who are like that, where it's like their sound is still old school, but like they're into like new, you know, like they don't really do the new music, but good. They're old school, into their old school like hip hop bag, you know?
Yeah, I like that. That's good. I forgot about Scooter.
Yeah. Okay. He's one of the other, he's like the recurring character that's like linked on the wiki, where it's like he's a major enough character where they've actually made him a page.
Yeah. Good call. Good eye. And then that does just leave one for the last one.
It does.
We'll see if you think it's a good fit.
If it matches, yeah.
So the last field is cosmology. These are people who are concerned with how the universe began and how it's going to end. They study the shape and the expansion of the universe on the largest scales. So I'd say the kind of half step between galactic astronomy and cosmology is the large scale structure of the universe, where you're studying galaxy clusters and the cosmic web, because you have to study that to understand the long-term behavior of the universe. There is a solid subset of cosmologists who are working on getting like one more decimal point right in some value, like the cosmological constant. And so that definitely is there. But there are also really cool cosmologists who are trying to figure out how the nature of dark energy is going to lead to the eventual fate of the universe. And they're trying to figure out how dark matter acted as scaffolding so that galaxies could form very early on in the universe when things were still really hot and were not without cold dark matter, it would be hard for things to collect into galaxies. So, there's that dual nature. They use a lot of large surveys and simulations of galaxy clusters and the cosmic microwave background. Some large surveys that are really popular. The Planck survey is a mapping of the cosmic microwave background, an update from the W map, which I think is the Wilkinson microwave probe something. I don't know. But Planck is the latest in a dynasty, a lineage of cosmic microwave background map surveys. Another survey is the Baryon Oscillation Spectroscopic Survey that's trying to study the baryonic acoustic oscillation. This is one of the largest scale features in the entire universe. Very early on in the universe, a pressure wave was sent through the entire universe because it was smaller. Early on. So a pressure wave could move through the whole universe. And that pressure wave created peaks and valleys that are still here, even though the universe has expanded. They're just really, really big. But if you zoom out in the universe, you can see that there are kind of ripples where there are peaks of matter distribution. So there's a lot of material gathered in these peaks, and then you'll see valleys of voids, and then there's going to be another peak in the matter distribution again. And that's called the baryonic acoustic oscillation. We can study it to figure out how things are moving really, really far away from us in the universe. Okay. It's a good yardstick for really big distances.
Okay.
And so those are surveys, and then there are really big simulations. The Illustris simulation was finished in 2013, but was kind of the gold standard for most of my time in grad school. It's a cosmological simulation that has started at the beginning of the universe, and then through equations of motion and other types of influence has step by step moved forward in time to the present day in a computer and figured out what the universe would look like at different snapshots in time up until today. And that was a huge collaboration. It took years to develop and to publish. And so it was really popular and is still used today. That's the Illustris simulation, but there are others.
How fast do you go through the simulation to get do you know? I guess there could be you could change the speed or whatever, but is it you can literally press play from the beginning and then see the changes? Is that what that means? Or is it more you have to plot in a date?
It's data. It's not a video.
Gotcha.
Yeah. But you could, I'm sure, make a video.
It's somebody could have made it one.
I'm sure someone has absolutely
might have
made a video of the data.
But when you say simulation, then the simulation is strictly data?
Yes. So the output of the simulation to an astronomer is not a video telling you what the universe looked like, but it is a massive data set with positions and velocities of millions of particles. I'm using that in quotes because the particles in a big simulation like this are going to be stars. But it has the positions and velocities, at least. There are probably other things that it includes, of all of the particles in the simulation at different snapshots in time. And that time step, I don't know what their time step is, but it could be every 1,000 years. But every 1,000 years for 14 billion years is many time steps. Yeah. For millions of particles that they're taking into account. Yeah, that's why it takes so long for these simulations to be published, because it takes a long time to develop the code to run it and then to actually run it. In my grad school work, I was writing and running simulations to simulate the orbits of 1 million stars in the Milky Way galaxy. And those simulations took more than a full 24 hours to run. So I can only imagine a full cosmological simulation on, even with really powerful computers.
That's a lot.
That's a lot. And yet, in 2021, I think, the Center for Computational Astrophysics and the Harvard Center for Astrophysics, they collaborated to make a suite of cosmological simulations. Not just one, but a whole suite of them where they tested out multiple different parameters so you could explore a simulation with one value for the cosmological constant and then another simulation with a totally different value for the cosmological constant and see which one matched your observations best. And that is called the Abacus Summit. And I imagine it takes a lot of storage. I imagine it's a huge data set.
Yeah. I wonder where they keep. Where is it? Is there a place? It's a resource, but there might
physical place.
It might be a data center somewhere.
No, not a data center, because it's not that it's actively doing stuff now. The simulations are made and the data is out there. They were using both of the collaborators, the Harvard Center for Astrophysics and the Center for Computational Astrophysics. They have their own computing resources. So for people, the cosmologists that I know or know of, the father of the Big Bang, he was also a father. He was a priest, Belgian maybe, German something. German, French, I don't know. His name was George Lemaitre. Lemaitre.
Yeah, Lemaitre.
Yeah. And people have been working towards the Big Bang Theory for a while, especially since Einstein published his theories of relativity. And then Hubble proved that the universe was expanding in the 1920s observationally. That was after another person, something Friedman, did a mathematical proof of the expanding universe. But in 1931, after all of that happened, George Lemaitre, he was the first to suggest what would have come before an expanding universe. And so he was the first to say, well, if everything's expanding outwards now, it must have started from an original tiny point. And he called that point the primeval atom, and he published the primeval atom hypothesis, and that became the Big Bang Theory.
A father. A Catholic, perhaps, father?
I don't know the denomination, but
still, that's a fascinating.
There was a lot of overlap with that once, where there were a lot of priests in astronomy, because they looked to the heavens.
Yeah,
and the Vatican has an astronomer. I've met the Pope's astronomer, or maybe I don't know if the new Pope got a new astronomer, but I at least met the last Pope's astronomer. His name was Brother Guy.
Wow. Mm-hmm. And it makes sense when I think about it, but I wouldn't have thought about it. Because it is like they do also have to do calculations for when things happen.
Yes.
You know, the ones that are based on astronomical movements and whatnots. I think Easter's one, but there are probably several more that I don't remember.
I'm trying to think of others too, and I couldn't.
Yeah, I'm blanking,
you're exactly right. So he was a father. Stephen Hawking. And then definitely not a priest is Dr. Chanda Prescott Weinstein, who is my favorite cosmologist, a theoretical cosmologist and particle physicist, because this is where it rounds back on itself, and the cosmology and the particle physics really overlap quite strongly. I'd say the reputation and the culture of cosmologists, knowing that they have those kind of two potential natures, is that either way, they're still kind of the glue of the community and the public sweethearts of astronomers. Because when I meet people who are interested in astronomy, a lot of the times they're interested in aliens. But all of the time, they are interested in, like, how the universe came to be. Like people really like astronomy for the big questions. How did we get here? Where is the universe going? Like, how did it start? How did it end? The alpha and the omega, like they love to know that shit. And so the public likes them or needs them, and it's almost like the rest of the field needs them to keep going, because if we don't understand the universe, like we can't understand planets or stars or galaxies or whatever.
That's true. Bestie, this has worked out so perfectly. And I did not plan it. I did not look ahead. But Sinclair is left, played by Kim Coles. And I love this because she is also kind of the glue of the group. She's the emotional one. She's the one that kind of like helps regulate people's emotions or like lift them up or calm them down or give them advice that's like simple but wise. Like that kind of character tends to be the like thinks really big, but like maybe accidentally or maybe like quirkily. Like she's that kind of character where she will say something like really sounding obtuse, but then it really means something deep. And so I feel like that connects here. There's something about Chanda's from our recent episode. There's something about her that gives me Sinclair vibes, but mostly because of the whale earrings that I believe they were wearing.
Their earring game is so strong.
Yeah, and so I think there's something quirky there that I love. Yeah, so Sinclair, which is crazy to think about, that she would be a cosmologist.
Yes.
But yeah, thinking really big and like being the glue that kind of keeps everyone together.
And her hair is big like the universe. It's
exactly.
Of all of the different subdomains, this was the only one that I had an inkling of who it would be, and it was also Sinclair. So I'm glad that worked out.
Yes. Amazing.
Thank you for connecting the dots to the living single characters.
This was so fun.
Which subfield would you do?
Great question. I feel like cosmology, which is funny because I am like most like Sinclair. What about you, bestie?
Well, I mean, you're cosmology and I'm planets, but really, it doesn't matter because interdisciplinary research is where it's at, and doing a PhD in planet, stars, galaxies, the intersection therein was really fun. So mix stuff up, cross the circle, cross the wheel, connect things, on opposite sides, and that is where the most interesting research can take place.
Indeed.
But no matter where on the wheel you are, you're still space. Bye.
We are living space.
Yes, we're living the twinkle life. Because we're stars.
Okay, cut the cameras. Pale Blue Pod is hosted by Dr. Moiya McTier and Connie Gibbs. Moiya created the show with the funny and talented Karine Caputo with help from the Multitude Productions team.
Our theme music is by Evan Johnston, our cover art by Shay McMullen, and our audio editing is handled by the superlative Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Instagram or check out our website, palebluepod.com.
I, Moiya, am GoAstroMo on all socials.
And I'm @ConStar24 on Instagram.
If you want to support our show, join our community at patreon.com/palebluepod or send this episode to your family and friends group chats.
We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
Thanks for listening to Pale Blue Pod. We'll be back next week.